All right, let's take a look at a few more examples of indefinite integrals of antiderivatives. All right, so the first one we see, it involves trig, also involves a quotient. Now, we don't have, I've already mentioned this before, we don't have a quotient rule to work with. So chances are, if we're working with a quotient, then we need to rewrite it somehow. So actually, examples A and B need to be rewritten somehow. Now, of course, there are some integrands that we know the antiderivative of. For instance, that happen to be quotients. Like, for instance, the antiderivative of 1 over 1 plus x squared, for instance. Well, that's, dx, of course. We know that the antiderivative of that is arctan x plus c. Why? Well, because we know the derivative of arctan is 1 over 1 plus x squared. So there are some exceptions to that rule that quotients need to be rewritten, but here we don't know. This, like 4 cosine x plus sine squared x over sine squared x, that's not something that we have memorized in our antiderivative list. So let's take a look. All right, so we have the antiderivative of 4 cosine x plus sine squared x over sine squared x dx. Now, my first hunch for something like this is to rewrite it as two separate fractions. So write this as 4 cosine x over sine squared x plus sine squared x over sine squared x, parentheses dx. Okay. Now, okay, obviously the second term simplifies to 1. It's sine squared over sine squared. This first term, though, it's not entirely obvious what we need to change it to. Of course, we could write this as 4 cosine x times, okay, what's the reciprocal, or what is 1 over sine squared x equal to? That's what? Cosecant squared, like so. And then, of course, plus 1 dx. But that cosine x times cosecant squared x doesn't ring a bell to me. So that means we need to pick a different way to rewrite this. And by the way, that's just kind of a common thing with antidifferentiation. You might have to try a couple different ways to rewrite until you get something that works. Antidifferentiation, indefinite integration, is in general way harder than differentiation. What I mean by that is I could pretty much give you any function and say take the derivative, and you could probably take the derivative of it, given enough time and if you're careful enough with your algebra. Antidifferentiation, not so. There are plenty of situations where antidifferentiation pretty much gets more or less impossible or super, super, super hard, even with very ostensibly simple functions. So let's try to rewrite this in a different way. We have 4, of course. Now, what if I wrote that as maybe cosine x over sine x times 1 over sine x? Then we have the plus 1. Now, would that help us out maybe? Let's see. That would give us 4. What's cosine over sine? That's cotangent, right? Yeah. I think this is going to help us because we have cotangent, and then what's 1 over sine? That's cosecant plus 1 dx. Now, we can apply the sum difference rule, and this is the antiderivative of 4 cotangent x times cosecant x plus, we need a dx, sorry. We're breaking apart, both terms need a dx. Dx plus the antiderivative of 1 dx equals, now let's apply the constant multiple rule to that 4. We can pull the 4 out and have the antiderivative of cotangent x times cosecant x dx plus antiderivative of 1 dx. Now, let's see. What's the derivative of cotangent cosecant? Now, you might recognize it more readily if I call it cosecant cotangent. Because what is a familiar derivative that is similar to this? What is the derivative of cosecant? Is it negative cosecant cotangent x? Now notice we have a positive cotangent cosecant dx. So if we had a negative cosecant cotangent, we would know that the antiderivative is cosecant, but we don't quite have that. But how can we fix that? Well, we could fix that by essentially putting a negative sign, like a double, think about it this way, put like a double negative 1 out front. A double negative is a positive, right? So I haven't changed anything. However, I can now use the constant multiple rule to factor in a negative 1 and put it right there. So now I can write, we have negative, so we left one negative sign out front, so it's negative 4, negative cotangent x cosecant x dx plus the antiderivative 1 dx. And now we know, okay, we have this integrand. We have negative cosecant times cotangent, which I know has an antiderivative of cosecant x. So I get negative 4 cosecant x plus the antiderivative 1 is just x plus c. So there we are. Again, if you're curious, take the derivative and make sure that you get, well, here's the tricky thing. So if you take the derivative, you should get that. But then as long as you agree that that is equal to that, then we should be good. Okay? Because we need to do a couple of algebraic simplification steps in between. Okay? All right, B, we have another quotient. So let's rewrite, much similar to a previous example. We have a polynomial on the top, and we have a single radical on the denominator, so it's probably best to basically do the same first step as with example A. We're going to say we have v squared plus 1. Oh, this is v, but notice we have all v's, so we just basically have a different variable to worry about. We have dv. And by the way, that's v to the 1/2 is the square root of v. And we can then immediately rewrite this as two separate fractions, v squared over v to the 1/2 plus 1 over v to the 1/2, like so, dv. And now let's apply the properties of exponents. So we have what? V squared over v to the 1/2. We can write that as v raised to the 2 minus 1/2 power. What's 2 minus 1/2? That's 1/2, otherwise known as 3/2. Plus, we can write that as v to the negative 1/2 power. Now, why did I even do that? I did that because we cannot apply the power rule of antidifferentiation unless the power function is on the numerator. Just like with differentiation, we could not apply the power rule for differentiation unless the power function was on the numerator. It would be improper to try to apply the power rule to a function that was on the denominator, like that second term is. Okay? So now that we've done this, we can apply the sum difference rule and say this is the antiderivative equal to the antiderivative of v to the 3/2 dv plus the antiderivative of v to the negative 1/2 dv. And now we have two individual power rules to take care of. Let's see, we have v, we're going to increase the power by 1, then divide by that new power, both times. Now we have v to the negative 1/2 power plus 1 over negative 1/2 plus 1 plus c. Oh, and what does that give us? Okay, 3/2 plus 1 is v to the 5/2 power. 3/2 plus 1 is 3 over 2 plus 2 over 2, which is 5 over 2. Now notice we're dividing by that same value, 3/2 plus 1, which means we're dividing by 5/2. But dividing by 5 halves, so v to the 5 halves divided by 5 halves is the same thing as v to the 5 halves multiplying by the reciprocal. Because remember, whenever you divide by a fraction, you flip it and multiply. So basically what I'm telling you is, instead of dividing by 5 halves, we simplify and multiply by 2/5 instead. Plus, or you know what, it might be negative. Actually, no, we're gonna have be positive here, because we have v to the 1/2 plus 1. That's the positive 1/2 power. But we're dividing by the same value, 1/2, but dividing by 1/2 is the same thing as multiplying by 2. And of course, we have your plus c. All right, so there we are. There's our nice final antiderivative. And again, we're doing that all with just our basic properties of antidifferentiation that we pretty much know simply because of our derivative list. Now let's look at C. Notice C is composite. Well, here's the thing. We will talk extensively about composite functions and their antiderivatives soon enough. And there's going to be a special method, kind of like we had the chain rule to differentiate composite functions. We're going to have basically an analogous chain rule to anti-differentiate those functions. And this is composite. However, we don't know about that rule yet. And so we can actually solve it a different way. And again, the general idea is to rewrite it so we can use the tools we have. Well, how can we rewrite this? Well, we have 2 plus y squared times itself. So just using algebra, we can say, all right, let's see, 2 plus y squared squared, that's 2 plus y squared times 2 plus y squared. Oh, didn't mean to do that. Here, let's fix that real fast. There we go. Getting too close to the ribbon. Flying too close to the sun. All right, equals. Let's go down here to not get too close. So if we just need to distribute, FOIL, if you like to FOIL, 2 times 2, 4. 2 times y squared, 2y squared, plus another y squared times 2, so that's 2y squared. Plus y squared times y squared is y to the 4th. So if we collect those two middle terms, that's going to give us an equivalent function, an equivalent integrand of what? 4 plus 4y squared plus y to the 4th dy. And now we have 3 functions that we can apply our known sum difference rule, constant multiple rule to, power rule, and be done. So let's see, we're going to take all the derivatives individually. Sorry, antiderivatives. So we have the antiderivative of 4 dy, of course, plus the antiderivative of 4y squared dy, plus the antiderivative of y to the 4th dy. And the last thing I'm going to do before I actually take the antiderivatives is to factor out that 4. So leave the first one alone. Actually, yeah, it's 4. That's 4 dy. That's just a constant. Then we're going to bring out that 4 times the antiderivative of y squared dy, and plus the antiderivative of y to the 4th dy. And now we're home free because we have 3 different antiderivatives. What's the antiderivative of the constant? Well, we just multiply by the appropriate variable, and here that variable is y, so 4y. Plus 4 times the antiderivative of y squared. So we increase the power by 1, 2 plus 1, and we divide by that same power, 2 plus 1. Plus y, power rule again, increase the power by 1, divide by that new power, plus c. And then if we just clean this up a little bit, we get 4y plus, okay, we have 4 divided by 2 plus 1, so divided by 3, times y cubed, plus y raised to the 4 plus 1 power, that's 5, divided by 5, plus c, and there we are. All right, so although that was a composite function, And in general, we're going to need to use something called U substitution or the chain rule to work with composite functions. That was a composite function that actually doesn't fit that method very well as it is, and it doesn't matter because we can even rewrite it by just algebraically expanding it, collecting like terms, and then using our basic rules that we have in our pocket already. Okay, so there's 3 more examples. We'll do a few more examples in the next video. Again, kind of like with derivatives, actually more so than derivatives, these just take a whole lot of practice because you have to just always, by practice, figure out, all right, there's lots of different techniques, and you get used to, okay, I see that function, I bet this technique will work, or I see that function, I bet this technique will work. But without extensive practice, you're not going to build that intuition. So more than ever with antiderivatives, it's super important to practice a lot. Okay, I know it's toward the end of the semester and we might be starting to get burnt out and stuff, but it's super important that we're practicing a lot every day with these. All right, I'll catch you in the next video.